A single wire is all that stands between your diagnostic tool and the vehicle's control modules in legacy cars. And some technicians out there usually treat this wire as any other wire in the vehicle. Understanding why your diagnostic tool is not communicating with the control modules starts by understanding the physics of that single wire, and that's none other than the kline. Mulungi Steven is my name, and I'm the head technician at Nana Auto Diagnostics. And I want to welcome you to part 2 of our 7-part series, which covers automotive communication networks. In my previous video, I covered the G1850 communication protocol, which was part 1 of this series. So if you missed that, please go and watch it. I have tagged the link in the description below. And today, we are going to be tearing the ISO 9141-2 communication protocol, which defines the kline and KWP 2000, which stands for Keyword Protocol 2000. And we shall begin by defining what kline communication is. So kline communication is a serial data transmission protocol primarily used in automotive diagnostics. It was developed by Bosch and uses a single bidirectional wire that allows diagnostic scanners to connect to the car's electronic control units in order to read error codes or DTCs, which stands for diagnostic trouble codes, reset parameters, and monitor live sensor data. Now let me make this clear from the very beginning. The kline communication protocol is only used for communications between the scan tool or any diagnostic tool and the vehicle's ECUs or electronic control units, or you can call them modules. This communication protocol is not used for module-to-module communication. So let's go ahead and define the characteristics of the kline communication protocol. And we shall begin with the physical layer. This protocol operates over one bidirectional wire known as the kline, with an optional line known as the L line. And this line is only used for system wake-up or initialization. The kline is designated to pin 7 on the OBD2 port, whereas the L line is designated to pin 15 on the OBD2 port. Kline communication may employ two systems: a single wire system where only the kline is used, and a two-wire system which employs the kline and the L line. Now, in a single wire system, the kline serves two purposes. One, bus initialization, and it also serves as a communication link between the diagnostic tool and the vehicle's control modules or ECUs. On the other hand, the two-wire system employs two lines, which is the kline and the L line. The L line in this case is used for initialization, or you can call that waking up of the modules, and the kline is used for communication between the ECUs and the diagnostic tool. If I plug in my scan tool or any diagnostic tool and can't communicate with ECUs or modules, where do I begin my diagnosis? Now it's important to know that both lines, that is the K line and the L line, have battery voltage. Now if you measure on the K line and the L line and you don't have battery voltage when the key is on, that should be the first red flag. So what happens is, if you're lacking the battery voltage on the L line, it means the modules cannot be initialized. In other words, they can't be woken up, because the initialization for a two-wire system occurs on the L line. So if you're lacking voltage, it means the modules, they will stay asleep, so to say. So you can't have communication still on the K line. Secondly, if the L line or the K line is shorted to ground, still you can't have communication in that case. And another thing that can prevent communication on this network is when one module or several modules have shorted to ground. Now what happens is, whenever we have communication on this line, the 12 volts are going to be pulled to ground. So in case we have one module that is already pulled to ground, it will dominate that line. So we shall not have any communication whatsoever on that line until you unplug that module from the communication line. That's when you will restore communication on that bus. So we shall look at those scenarios and more when we move on to our practical session, where we shall be able to observe the waveforms and subject the network to various faults. So keep yourself on the channel, because more is still coming. It is also important to know that pin 15 is not universal. Now what do I mean? It was allocated to the L line in the older vehicles, or what we know as legacy vehicles. But for the newer ones, that pin may be allocated to something else. So you need to read your schematics, or what most of you know as wiring diagram, to know what is allocated to that pin before you can even start your diagnosis. Still on the characteristics of K-line, you're going to look at signaling and voltage. Now this communication is based on battery voltage, and it idles at high, which is 12 volts, and is active when pulled low, which is to 0 volts. And this is true for the K line and the L line. Now the data rate is about 10.4 kilobits per second, and the communication type it employs is half duplex. In other words, devices can transmit in both directions, but only one at a time. If you want to understand duplex, I have a separate video which talks about that, where I discussed half duplex and full duplex. I've tagged the link in the description below. Next, let's look at the topology. Now the K-line employs point-to-point topology, which is based on a master-slave architecture. Now what do I mean? When you plug your diagnostic tool into the OBD2 port, that tool acts as the master, and the control modules will act as slaves. So in that kind of arrangement, the communication is always initiated by the master, which is the scan tool, and the ECUs or the modules will respond to the request of the master. So if you are to carry out any diagnosis on the kline network, you must have communication on that network. Otherwise, you're going to be seeing 12 volts, which is battery voltage, on that network. So if you're diagnosing, you must attempt to communicate. And this can be in form of a request of live data, or you try to obtain some data from a module. But all in all, you must have communication between the scan tool and the module to be able to see communication on that line. I've been talking about initialization, or you can call it waking up of ECUs. But how is it actually achieved? So join me as I cast more light on how initialization is achieved. In this video, I'll be explaining how initialization is achieved in the kline communication protocol. And this is usually of two types. We have the slow initialization and fast initialization. Now, the slow initialization is usually used in the kline communication, whereas the fast initialization is used in KWP 2000, which is Keyword Protocol 2000. So let's begin by looking at the slow initialization. And we know that kline employs two systems, a two-wire system and a single-wire system. In a two-wire system, it uses the L line for initialization and the K line for communication between the scan tool and the ECU, whereas in a single wire system, the K line is used for both initialization and communication between the scan tool and the modules. So I'll begin with the two-wire system. Now, in a two-wire system, we have our DOC. Yeah. Now the DOC is the data link connector, or you can call it the OBD2 port. And my focus here will be on pin 7 and pin 15. Now pin 7 is for the K line, and pin 15 is for the L line. So what happens when you connect your scan tool? When you have your scan tool connected here, it will attempt to communicate with a module. Let me take, for instance, we have the PCM, which is the powertrain control module. So what will happen in a two-wire system? The initialization or the wake up signal is transmitted via the L line. So you're going to have initialization from the L line, and that is the on pin 15. So what happens is this initialization is usually transferred at a low speed, usually at 5 bits per second. And that is why it is known as a 5-bound rate transmission. And once this initialization has been sent the kline will now switch to a higher speed, preparing for data transmission, which will be around 10.4 kilobits per second. So what happens is, whenever this initialization code has been sent to the PCM will acknowledge that it has received that code and will have to send back 2 data bytes. Let me have this as byte 1, data byte 1, and data byte 2. So these are going to be sent back to our master. In this case, the master is our scan tool, and of course the PCM is our slave. So once the slave or the PCM has acknowledged that it has received the initialization code, it is going to send 2 data bytes back to the master, which is our scan tool. And then the master will invert data byte 2 and send it back to the slave to acknowledge that it has received the feedback from the PCM, and that will complete the initialization stage. And as you can see, this entire process takes about 2.5 to 3 seconds, and that is quite a lot of time when it comes to communication. So let me summarize this. So what happens is, whenever you connect your master, which is your scan tool, to the OBD2 port, trying to communicate with the PCM, which is the slave, the scan tool will send an initialization code on pin 15, which is the L line, and this is usually at a speed of 5 bits per second to the PCM. Now the PCM will acknowledge that it has received that initialization code and will send 2 data bytes. These are data bytes. Remember, a byte is a group of 8 bits. So it will send 2 data bytes, and the master, which is the scan tool, will invert one of the data bytes and send it back to the PCM to complete the initialization process. Next, we are going to look at the single wire system, and this system only employs the K line. It does not use the L line. So initialization and communication are both achieved on the K line, and this is how it operates. So if we have our DLC, I will focus mainly on pin number 7, and that pin is for the K line. Now if we have our scan tool here and we attempt to communicate after we've connected our scan tool with the DLC, this is the same as OBD2 port. Now an initialization code is going to be sent to our module. Let me use PCM, and this is acting as our slave node. So once the initialization code has been sent, this is usually sent at a lower speed, such as 5 bits per second. That's why it is known as a 5 baud rate. Once this initialization code has been sent, the speed of this bus is going to be shifted to a higher speed to prepare for data transmission, and that is usually at 10.4 kilobits per second. So what does it take from here? The initialization code is sent at a lower speed, 5 bits per second. Once that has been received by the PCM, the scan tool will shift the speed to a higher speed of about 10.4 kilobits per second to prepare for data communication or data transfer between the scan tool itself and the PCM, which is acting as our slave. So what will happen once this initialization code has been received by the PCM will send back 2 data bytes. Let me actually have data byte 1 and data byte 2. These are data bytes. So once these data bytes have been sent by the PCM to the scan tool is going to invert one of the data bytes. By inverting, I mean if a data byte, let me say, is 100101110. By inverting, I mean it will change a 1 to a 0. So if this was a 1 that was sent to the scan tool will invert. Where there is a 1, it will put a 0. Where there is a 0, it will put a 1. Like that. So that is what it means to invert. So it will invert one of the data bytes and still send that inverted data byte to the PCM or the slave to signal that the communication has now been established and initialization is complete. So that's how initialization is achieved on a single wire kline communication bus. And as we've seen, it's not different from that of a 2-wire, only in this case 1 wire, which is the kline, is utilized. Now, because this process is quite long, that's why it is known as slow initialization, and usually takes 2.5 to 3 seconds. Now that is quite a lot of time when it comes to communication, and it's because of that the KWP 2000, which stands for Keyword Protocol 2000, was introduced to reduce on that initialization time. Next, let's look at how initialization is achieved in KWP 2000, which is Keyword Protocol 2000, and we shall see that it is completely different from the way it is attained the kline protocol. So when we are looking at fast initialization, and this is KWP 2000. Now in this communication protocol, when we connect our scan tool, remember our scan tool is acting as our master, to the DLC port, or you can call it the OBD2 port. In this case, I'm focusing on pin 7. And initiate communication between the master, which is our scan tool, and any node. In this case, I'll consider the PCM, which is the power train control module, which is acting as our slave. Now what happens is, at pin 7 here, which is our kline, we must have battery voltage, which is 12 volts. What happens is, whenever we want to start communication or initialization between the scan tool and the PCM, the voltage level on this line, which is the K line, is going to be dropped from 12 volts to 0 volts for about 25 milliseconds, and then that voltage will be raised again to 12 volts for a period of 25 milliseconds. Now, when that happens, it means the initialization has been completed. So the voltage on the K line will be pulled down for a period of 25 milliseconds and pulled up for a period of 25 milliseconds. So that will complete the initialization process. And all this is happening at a speed of 10.4 kilobits per second. So you can see that this process takes about 50 milliseconds and may extend to a maximum of 100 milliseconds, as compared to the slow initialization, which takes place for a period of 2.5 seconds to 3 seconds. Now that is quite a lot of difference when it comes to communication, and it's because of that this initialization is considered as a fast initialization. And in the newer models, you always find this type of communication. Someone out there may be asking, as a technician, do I really need all this? Yes, you do. Because if you don't understand how the system works, or if you don't know what to expect on the waveforms on that network, it will be hard for you to know whether the master is transmitting or whether the slave is responding, and all those components will tie together. When we start our practical sessions, you'll be able to see all these waveforms and how they appear whenever we have or whenever we don't have communication on the network. Thank you for joining me in this video, which has been part 2, and in part 3 we shall be looking at the LIN, which is a local interconnect network.